the Maxima formula and small angle approximation. After looking at the interference pattern caused by the double slit interference and the diffraction grating, a relationship was seen for where the maxima or the bright lights occurred. The relationship depends on the distance between the slits, d, the wavelength of the light, lambda, and the angle theta from the center of the slits, an integer m, counting which maxima you have. There's an equation here that describes it. D sine theta is equal to m lambda. That will give you the location of the maxima, which is where you have your peaks, your brightest light. Using triangle properties, we find a simple geometric relationship for the maxima location. We have our light coming from here, and then it's hitting a screen, and this is where we can read off where the maxima are. That's where the bright lights are, and the minima. So the location of the maxima, we can find tan theta is x over L, opposite over adjacent. For small angles, and a small angle is anything less than 15 degrees. However, every problem in this course will be considered a small angle, so we can get rid of the sine function. So we're going to make the approximation, and here's the small angle approximation, that tan theta is approximately equal to sine. So we say tan theta is equal to sine theta, which enables us to claim sine theta is now opposite over adjacent, x over L, just for small angles. So let's go to the next slide to complete this. We then substitute into the maxima condition equation and rewrite it in terms of x with no need to measure the angle. We start with the maxima condition, d sine theta equals m lambda. On the previous slide, using the small angle approximation, we showed that sine theta equals x over L for angles less than 15 degrees. Substitute in, we have d x over L is m lambda, and finally x, which is the location of the maxima, is m lambda L over d. The equation for the interference pattern for the diffraction grating is the same as for the double slit experiment. The wavelength dependent of the maxima location is shown here. You can see the different colors showing up. Since each color has a different wavelength, each color will appear at a different distance from the center. We call those spectral lines. And here's where we were talking about the order. M is equal to 1 for this group of lines. Then M is equal to 2. That solves for where these lines show up. And our diffraction grating, here's a little blown up view here. D now is the distance between each of the little etchings on your glass slide.